Okay, so let's get back to derivatives. That's our goal here. And there's several different notations that all say find the derivative. So this is from your book where they list some of the different notations. So I like the prime notation the best, and you read this: f prime of x. So if your function's name is f, its derivative is called f prime. And then if your function's name is y, its derivative would be y prime. So then we have another notation that's called Leibniz notation, and it says dy dx. So this is courtesy of Leibniz. Oops, he doesn't have an E on the end of his name. And you read this dy dx. dy dx. Then this last notation says if I do the derivative notation first, it still means the same thing. This d, it looks like d over dx, but you don't read it that way. You say d dx. So you say d dx of f of x. Okay, so those are just some different notations. My strong preference is the prime, but make sure your primes are really large and visible. Don't make them little tiny dashes that are hard for you and I to read. So there's some rules that have been developed, and they're not just made up rules. Somebody did a whole bunch of derivatives the long hard way like we were doing it and said, I want to do this once for everything like this and see if there's a pattern. So they found the pattern and they're passing it on to you, so you get to use these rules of derivatives now. So when we're talking about polynomials, let me just write a random polynomial. It has several parts to it, so let's give them their names. Each part that's being added or subtracted is a term. And at the end, if there's a number being added, it's the constant. So the first rule we're going to have is the constant rule. And then you see that the polynomial function is made up of the sum of a bunch of power functions. So the next rule we need is the power rule. So you see the power function x to the fifth and the power function x cubed. Then the next rule we need is the constant times a function, because we have this 2 multiplying the x to the fifth and this -4 multiplying the x cubed. Those are constant multiples. They're constants multiplying the x part of the term. And then the last part we're going to look at is this is a long sum. It's 4 things added together. So we're going to start with the constant rule. And this formal math language says if f of x equals k, some number, so let's pick 3, then f prime of x is 0. So let's see why that would be. Let's draw a graph of, let's see, f of x is interchangeable with y. So we'll draw the graph of y equals 3. Oh, it's a horizontal line. And what is the slope of a horizontal line? The slope is 0. Well, the derivative is the slope of a line for lines, right? So the derivative has to be 0 for a constant. And let me see if I can help you understand why that would be. If I have some polynomial function and I write the same function plus 7, all it does is shift the graph upward 7 without changing its shape. So the adding of a constant at the end does not change the derivative, and so its derivative is 0. Okay, then let's do the power rule. So if I have x to the n for any number n, so suppose f of x is x cubed, then f prime of x is, bring that exponent down in the front, write the x to the new power 1 smaller. So if you do the derivative the long hard way with x to the n in general, you can prove this. So it's not a made up rule. It's a pattern that someone noticed and has given to you and call it a rule. So this rule applies to any number n, including fractions and negative numbers. So let's do some more practice. If f of x is 3x to the 4/3, oops, let me not put the constant multiple yet. Suppose it's just 3x to the 4/3, then f prime of x is, the exponent comes down in the front, 4/3, x to the power of, subtract 1 from 4/3 to get 1/3. Okay, so let's do another example of, suppose I have x to the negative 1/2. Then the derivative is negative 1/2, the exponent comes down in the front, x to the new power of negative 3/2, which is, negative 1/2 minus 1. So no matter what the exponent is, the exponent comes down in the front and becomes a multiplier. Write the x, and then write the new power that's 1 smaller than the exponent you did have. Okay, then the next rule is the constant times a function rule. And this formal math language says, if my function looks like 4 times x to a power, then my derivative is going to be the derivative of 4x to the 3rd. This property says the 4 comes outside. So if you think back to how you did the derivatives the long way, we're basically saying you could factor out the 4, put it over to the side, do all the work, and then put the 4 multiplier back on at the end. So this is a power rule problem. So I have 4 times the derivative of x cubed is 3x squared. So that's going to give me 12x squared. Okay, so I'm going to pause there and come back and do the sum and difference rules and then finish off.